Let's talk about conic sections. Now, conic sections, think of a cone, right? And this is just a sketch. You have a cone and you have another cone. There's a reason why I'm using two here. There's a very good analogy where imagine you take a plane like this, right? Take something that could be considered rectangle. And a conic section basically would be is a curve that is obtained as the intersection of the surface of a cone with a plane. Okay, that intersection. So if you put that cardboard, imagine if you put it through here, right? That would create a certain intersection. Again, this is not drawn to scale, but when we put that, we would get some sort of a cross. You look at it, you have this intersection of a circle if you put it straight out, right? And then imagine if you move this up and you move this down, so you tilt it. Imagine if we tilt this cardboard, right? If we tilt it and we kept tilting it, what's going to happen is this. First, you had a circle, right, when you put that out there. So the intersection would create a circle. Again, imagine you have this cone and then you put the cardboard, but now let's tilt it upward, right? So now we have a different shape that looks more like an ellipse. So you had a circle when you just put it through and it's even with the cone. Then you have an ellipse. And then you have something we call a hyperbola. And the last one is called a parabola. So those are the four typically in your textbooks they would list as conic sections. Some books might only put three: the ellipse, hyperbola, and parabola. But the circle is one that we can discuss in this context as well. So it's a special type of ellipse, basically. If you think of people like Johannes Kepler back in the day, they talked about the elliptical orbit of the planets around the sun. It wasn't circular, it was an elliptical orbit, right? You think of an ellipse, which is different from a circle, of course. So the conic sections, I'm just introducing how we derive these four special cases, or three cases with a special case of the fourth one. So we have circles, we have ellipses, we have hyperbolas, and we have parabolas. Now, I would recommend, this is usually in an Algebra 2 class or pre-calc, but I would recommend that if you want to dive deeper and enjoy the discussion, you can, again, look at a video on conic sections. But specifically for standardized tests, the ones that I would highly recommend are like your circle, the equation of a circle, x squared plus y squared is equal to r squared. If the circle has 0, 0 as the center, so the origin, then the radius, which is r, would just be this r squared here. So that's the equation of a circle with the origin being 0, with the origin being the center, sorry. We also have situations where we have x minus h squared plus y minus k squared is equal to r squared. That occurs where your center is at a different spot, right? And h and k represent that center. So that's the equation of a circle with the center at a spot that is different from the origin. So it's good to know the equation of a circle. It's good to know the equation of, let's review the equation of a parabola. That equation that we're looking at now will be y is equal to a into x minus h squared plus k. So again, it's good to know our equations. It's good to recognize what you would be dealing with these different situations. So we have the equation of a circle. We have the equation of a parabola. Let's look at another one here. We have the equation of a hyperbola. So we'll look at hyperbola and the ellipse. The hyperbola is actually x minus h squared minus y minus k squared. So both of these have, this one has a squared and this one has b squared, and they're equal to 1. So that's the equation of a hyperbola. hk is the center, is still the center, similar to with the circle. And then a is the distance from the circle to the vertex of each branch on the x-axis, and b is this vertical distance from the vertex of each branch to an asymptote. Now, what do hyperbolas look like? We can look at a situation where you see a sketch of a hyperbola, and you would see it's the one where you have we have sort of these asymptotes looking things here, and we have that and we have that. So we have the asymptotes, and then it comes out that way. So let me draw a better picture of the hyperbola. So hyperbola. So let's say you have the center over here, and then you have, we draw this out, We draw that out. And then we have this and that. So that would be like a hyperbola. Now, a parabola you're familiar with. You've seen it with quadratics. That's important. And then an ellipse you've also seen, which is, again, more like think of the planets going around the sun. So we have a hyperbola. We've looked at the equation. And now, looked at the equation of a circle. We've looked at the equation of a parabola. We've looked at the equation of a hyperbola. And now let's look at the ellipse. For the ellipse, we have its unique equation, which is similar. If you look at the one for the ellipse, you would notice that it's very similar to the one for the hyperbola. So you basically have x minus h squared minus y minus k squared is equal to 1 divided by a squared divided by b squared. And for the ellipse, it's x minus h squared plus y minus k squared is equal to 1, but then divided by a squared divided by b squared there. Very similar formulas. If the ellipse has the center at the origin, then it would just be basically x squared over a squared plus y squared over b squared is equal to 1 if it is at the origin, if the origin is the center of the ellipse. About h and k sometimes that is tricky for people, and that is when you're dealing with a situation like this, for example, where you have the equation of a circle, which is one that I highly recommend. If you're going to memorize your equations, make sure you remember the one for the circle especially. But if you have a situation like this and I tell you x minus 3 squared plus y minus 4 squared is equal to 9, right? And imagine this is 3 squared, which is 9. So my radius is technically 3. Now imagine over here, and if I ask you what is h and what is k, well, h is 3 and k is 4, right? Because when I plug in those numbers, it's still leaving me in the form of x minus 3, right? Because this minus was there originally. So this would be h. Now, if this was x plus 3 squared, and I ask you what is h, h is actually negative 3. Because when it was plugged in, it changed the sign to a positive, meaning that it was negative 3 to start with. So that's important. You probably see this in graph transformations, where we ask you, for example, if you have y is equal to x squared, this is just a sketch, and I ask you what is y is equal to x minus 4 squared, you might remember that we actually moved that graph to the right 4 times. And someone would say, well, why is that? Because the default equation was like this. So the h would have had to be a positive 4, which caused the graph to move to the right 4 times. So when you see this negative, don't allow it to make you think you're supposed to move to the left, because that is what the default one comes with, right? So you have y is equal to a into x minus h squared plus k. This is just something to help you remember, review, that when you have graph transformations, we sometimes will be moving in the opposite direction from the sign that you're looking at. So x minus 4, we're moving to the right 4 times, because h by itself was positive 4, which is why we would move to the right 4 times. Now, if this was plus 2, you would move up 2 times, right? So you see how the 2 there helps you. You move up 2 times. That's more straightforward with the k. Again, this is an introduction, but please, if you have any questions on a specific concept, don't hesitate to send an email. Have a wonderful day.